Typing started.
Okay, I'm also going to switch to the e-board in case we'll need it. So yeah, what do you want to go over first?
First, I'd actually like to go over one question.
Okay, you said one question in the Moon Lab?
The Mercury Lab. I do want to focus mainly on the moons and asteroids, but there's one question that I.
Oh, okay. Yeah. So, which question was that?
Question 11.
Oh, okay. Yeah, calculate the average rotational period for Mercury from the 4 values. Did you get 4 values?
Yes, I have my first value, and you want to go from like the left to right. Velocity.
Let's see. When you ran the CLIA lab, it gave you 5 spectra back, right?
Yes.
Yeah, one is just one peak, which is from the subradar point, and then you get 120 microseconds later than the second one for, so you say 120, I think is, yeah, I don't know how the numbers exactly go, but yeah, like I think every 90 microseconds you get another data set, and each of those have 2 peaks, right?
Yes.
So like a left peak and a right peak. Okay, and did you fill in the data table for the 4 time slices?
Yes, I did.
Okay, and well, actually I'm wondering, you may have already, yeah, number 11, you may have already that might be one of the calculations you do along the way. So you get 4 different values for the equivalent speed, like the 1, 2.
Which exact different values are you explaining for?
Say again?
You said that you asked me if I have 4 different values, but what particular values are you referring to?
It's a little bit hard to understand your phone. I'm sorry.
I'm fine.
I'll turn off my speaker here a little bit.
Okay.
Okay. Okay. So you said you got 4 different values for the speed.
No, I was repeating what you said.
Oh.
I just had 4 different values. What particular values are you?
Yeah, you're still breaking up a little bit. Well, I'm wondering if I can. Yeah, let me pull up a sample calculation. The one that I also had sent. Maybe you could type in your question because it was still breaking up a little bit. Yeah, okay, I'm just gonna go to my mail now and I'll try to capture it as an image, and then I can pull it up into Wimba. See. Saving it now.
Okay, hello.
Okay.
Can you hear me? Better?
Yes, I can hear you.
Okay, good.
Okay. Okay, let me see if I can import the image now.
Okay. It's question 10. The question that we're working on is 11. If 11 is in one of the, I thought it was something like a different calculation. But it's in equations that you listed for all those possibilities, then I do have the answer.
Oh. Okay.
But you could still go ahead and show me.
Yeah, I just found it. Okay, let's see. Yeah, do you see it now?
I do, but which one in that?
Well, yeah, well, what you're looking at here, these are basically the calculations for the rows of the data table. And, well, it turns out, well, what I've labeled question 10, actually I should have labeled that. What? No, that's correct. No, that is question 10.
Mm-hmm.
Yeah, so that's how you calculate the rotational period, and you get an answer in seconds. And I've done this calculation here, the sample calculation, just for one time slice, for the 120 microsecond time slice. So if you repeat all that calculation for the 210, the 300, and the 390 microsecond return signals, then you'll get slightly different rotation period for each. So let me just circle that. Oops, I didn't do it. I'm just undoing that. Okay, let me just do this differently. Okay, I guess I'm not really good with my fingers tonight. Okay, so you would get a rotation period in seconds for each one of the time slices. Okay, and then in question 11, then you take the average of those four values.
So, Do we do, the first one that I did was for 120, and I used row 9, the first number in that, to do my calculation. Do I continue it for each of those, like 210, 300, 390?
Yeah, you're calculating a rotational period in seconds for each of those. So you should get a value like something times 10 to the 6 seconds, like 4 different values of those. And then you take the average by adding them all up. So yeah, value 1 plus value 2 plus value 3 plus value 4, and then divide by 4 because you had 4 different values.
And that'll be our total for the calculated average.
Yes, for question 11. That's still in seconds, so you still have to convert that to days.
Convert to days.
Yeah, and then you just divide, whatever number you get in seconds by the number of how many seconds there are in a day. I think they give that. Yeah, the number of seconds per day is 86,400. So whatever your average winds up being, you divide by 86,400.
Okay. So you said add all the values up and then divide by 4 and then convert the seconds into how many seconds there are in a day.
Well, that's already been done for you. In question 12, they actually give you the numbers in seconds already.
Okay, so well then the 4 values divided by 4 and then just divide by 86,400.
Yeah, I'm going to write that out here too. Yeah, so in question 12, you're just going to, and let me just write that. So there are 86,400 seconds per day. So then you would just convert your P rotational in seconds and divide that by 86,400 seconds, and that'll give you the rotational period in days. So that's in question 12.
Okay. Well, I was going to start it too, so I know I should have that right.
Okay, I'm just going to draw an arrow here to show where that goes. Okay. Yeah, how about 13? Are you okay with that, or do you want me to go over that?
I just when I did the slides, I just noticed that one of my questions was answered, and I noticed that was number 11.
Oh,
I believe that I did 12, 13, and 14 correctly.
Okay, all right.
Okay. All right. Well, then we can start on the asteroid lab.
Okay. So, have you already started on that, or?
No, I didn't start. Well, actually, there was that I had on Jupiter before we go into asteroids.
Oh, okay.
I've started on the Jupiter, but I'm concerned that I'm actually doing it right.
Oh, okay.
And
which
let it start.
Go ahead. I'm sorry.
That's fine. I am concerned with those things. I'm actually drawing out the figures, like when you say to write where the great red spot is, or the white oval, or the brown oval.
Oh.
I'm just really guesstimating where they are. I know that I have pictures online for us to view, but I just didn't know if it was supposed to be like scaling and then like estimating it back onto the paper that we're writing.
No, I mean you can eyeball it. Yeah, in that sketch, you can just eyeball it, like on the worksheet, the Jupiter worksheet on page 12-9. Yeah, you don't have to accurately measure it and put down the exact position. I mean, you can just eyeball. Okay, that's roughly where they are, and so with the round ovals, roughly in the north. You want to narrow it down a little bit. The correct belt. And then the white ovals are sort of, just in the zone and belt to the south of the great red spot. But you can eyeball their positions.
Okay. All right. Well, then I won't have any other questions about Jupiter. I know I got kind of scared.
Yeah, that was for the sketch. Yeah, for the sketch, yeah. It's just later, you want to measure them for the calculations.
Okay. That's why you think I've been understanding.
Okay.
Okay. Let's move on to the asteroid lab. Okay. Oh no! Do we need the CLIA website for this?
No. The asteroid lab is on the GPC website. It's the same website as the Kepler lab. Were you able to run that?
I'm uploading it right now.
Okay.
I'm actually at the GPC campus. Because I had issues with the CLIA website and trying to do it on my computer. So I've always just used the computer lab, and they have like every single one on there, and you'll never run into any problems. But I'm like sitting outside the library.
Yeah, are you on the Decatur campus or?
Yes, the Decatur campus.
Oh, okay. Yeah, the lab supervisor has made sure that they're on the computers, I think in the LTC.
LTC.
Yeah.
Yes, that's where I stay. And the library computers have them as well.
Oh, yeah, well, that's nice.
Yeah, because I remember the first time I tried to download it to the lab, I think it took me 3 hours, and I got it on my computer. For some reason, it's very confusing.
I mean, the company has written these labs a while ago, and of course, they're updating them. But then, the operating systems are being changed and, whatnot. So I guess it's kind of hard to get them to run on 64-bit computers or with a Windows Vista system, and then, there are patches to work around. But yeah, it gets really complicated.
Okay, let me open this up. Asteroids, okay. All right, well, I'm on the University of Georgia Light Curve Lab.
Okay. Yeah, and there are 9 random asteroids and you'll get one of them. So that's why the first question is, what is your asteroid number?
Oh, okay. They have that number right there. Okay.
Yeah, and above the graph, you see how an asteroid might look when it spins. that it's sort of oddly shaped like a potato, and, sometimes it faces you with the wide side and sometimes with the narrow side. When it faces you with the wide side, then you'll get a maximum, and when it faces you with the narrow side, you'll get a minimum. So the pink thing to the right of it is the light curve, and the yellow is supposed to be where the asteroid is in its rotation. But because it has two wide sides and two narrow sides, and it is oddly shaped, they can be different. So you have two different maxima and two different minima.
Minimums. Okay.
Yeah, maybe what I might do, let me go ahead and share my desktop so we can both look at the same thing.
Okay.
And then, of course, you also have your numbers that you can work with then. But yeah, if I share my desktop, then it'll be recorded by the archive, and everybody will see what we're talking about. Okay. Okay. And do you see my version of the asteroid lab now?
Yes, ma'am.
Okay, great. Which number asteroid did you get?
I got 1.
Okay, I got 9. But you're doing it. Say again.
I was going to ask if there's any possibility to make the screen wider, but I don't think you can. I think it's just limited on my computer.
The WIMBA screen.
Yes.
Yeah. Let me see. Even if you maximize it, I think it winds up being a certain size. Well, I suppose you could try to maximize the WIMBA window, and you might get it a little bit larger.
Well, yeah, it gets a little bit wider, but the length won't change, but it's fine. I can still see it. I'll just have to scroll up and down.
Okay, but yeah, again, on the left side here, it shows the rotating asteroid, and you can see how it's really oddly shaped. It has two different wide sides, which account for the maxima whenever a wide side faces us, and it has two different narrow sides, which account for the minima when the narrow sides are facing us. So this is just sort of an illustration.
Okay.
Yeah, okay. I wound up with the number 9. You wound up with the number 1. So, yeah, there are 9 different possibilities that you can get. So that's why when you do the lab, you want to take all your data in one sitting, because when you leave the page and you come back in, then you'll get a different random number. And your chances are one out of 9, to get the same one again. So, okay, and then you can navigate the site by grabbing those lines and just click and dragging them. So the second question, the time between two successive minima, you would grab, one line, try to align it with the minimum, or also sometimes the minima are asymmetrical. So you can also put it where you put the V, you can imagine the minimum looks like a V, so as if you're splitting the V in half. And again, I'm taking ballpark figures, if it's close to the figures that I have on file, then, that you'll get the credit. Okay, so then the delta number here shows how much time is between the two lines. So right now I have put my lines on 2 successive minima. So the time between them would be 1.86, and that's in the unit is in days. So this would be the answer for question 2 for my particular asteroid. What? Yeah, 1.86. So that's for asteroid number 9.
Okay.
Okay, but as you can see, that is only half a rotation period because it only goes from, maybe the left odd-shaped narrow end to the right odd-shaped narrow end. So the full rotation period would actually be twice that number. Now the question 3 is to find the rotation period by multiplying the time between 2 successive minima by 2. So 1.86 divided by 2 would be the answer for number 3, or whatever you get for your number asteroid.
Okay.
Yeah, so 3 point, probably something like 3.72. Something like that. And of course in science, we always like to measure things different ways, or, and then take the average or something. So another way, what you could do also, and that's in number 4 now, place one vertical line on the left. Say again?
I have a question for you, Newborn. You said that you just take 1.86 divided by 2?
Times 2.
Oh, you said
Yeah, so you want to double it. Mm-hmm. Yeah, because the time between two. That's right. Yeah, so you just have, if you envision a football, and you label one pointy end of it 1 and the other pointy end of it 2, then from one minimum to the next minimum would just be like spinning the football from the 1 until you see the 2. So you only go through half of a rotation. And in order to spin it back to the 1, you'd have to go and drag it back to the same type of minimum again. But instead of measuring one full rotation period like that in number 4, we're going to place, one vertical line on the leftmost minimum and the other on the 2nd, 4th, 6th, and so on minimum to the right. So every other minimum represents a full rotation period. Now that also depends on the number of asteroids you get. Some asteroids rotate really fast, so you get a lot more minima, and other asteroids rotate really slow, so you get fewer minima. And I think number 9 is probably one that rotates a little bit slower. So what I'm going to do, since I'm not sure if what I'm seeing here at the very left, T0, if that is a minimum or not, I'm going to start, with the, first minimum where I see the curve dipping down and coming back up. And then I go to the alternate minimum after that, and, the alternate minimum after that. So that means I have a total of 2 full rotation periods in here. So if I read the time now, the delta, I'm reading 7.6 days. From looking at my graph, that is the time for 2 full rotations.
Okay.
So then this time I'm going to divide it by 2. So the 7.6 I'm going to divide by 2, so I get the time for 1 rotation. And 7.6, let's see, divided by 2 would be something like 3.8. So that's pretty close to 3.72. So either way we determined it, both of these numbers are in the ballpark, so they should match up. Your result from number 3 and your result from number 4.
Okay.
Okay. Yeah, I guess we can move the blue and red line out of the way again, because we'll be using the purple line now. Let's see, for number... Oh, okay. Yeah, before we go to number 5, there's a figure on page 13-10. Actually, there are 2 figures on there. There's a top figure that is figure 1, and a bottom figure that is labeled figure 2. Do you see the figure 1?
I'm sorry, on which page?
13-10. So it's almost at the end of the lab, of the asteroids lab.
Okay, yes, I see it.
Okay, yeah, so the top figure, figure 1, you have, one sketch that is labeled maximum, where the little circle that's already there is supposed to represent Earth. And then, so it's Earth's orbit with the Earth in it, and then it's the asteroid's orbit, and you're just supposed to make a little, like draw a little football, as if someone who's standing on the Earth circle, who's looking directly at the football, would see the wide side of the football. So reflect most of the light back to that person. And then the second part of figure 1 would be the minimum position, where you also have the Earth orbit with the Earth circle, and then to the right of it, the asteroid orbit. And again, just across from the Earth circle on the asteroid orbit, you want to draw the football again, but this time so that somebody who's on the Earth circle would see like one of the pointy ends. So one of the narrow sides is facing the Earth, and we would get the lowest amount of light from it. Okay, yeah, and then you just take a picture or scan it in and send that figure to me. Okay, and then we can go back to number 5. Number 5 is if your asteroid's axis of rotation were perpendicular to its orbital plane, and if you were standing on its equator, approximately how long would it be between sunrise and sunset? In this case, well, you want to think about, okay, if I compare that here to Earth. So if you were standing on Earth's equator, how much time would it be? And I mean, our axis is not exactly perpendicular, but it's pretty close to perpendicular to the orbital plane. But how much time on the equator do we have between sunrise and sunset? Well, if one day is 24 hours, then the time between sunrise and sunset
would be 12 hours.
Would be 12 hours. So we're looking for half a rotation period. And of course, our asteroid, the number asteroid that we have doesn't rotate once every 24 hours, but it rotates once every 3.72 days. So what we want is half of that. So if you were standing on the asteroid, let's say you were standing on one of the pointy ends of the football, then if you pass the sun when the sun rises, well, maybe it might not be such a good example because the pointy end, well, I don't know. Well, okay, if the asteroid were more spherical, like the Earth, then the time between sunrise and sunset would be half of its rotation period.
Okay.
And that's basically the same number that we measured initially for question 2, the time between two successive minima.
Okay, and then that would be the same as for number 5.
Yeah, so for asteroid 9, that would be 1.86 days, which was half a rotation period. So if you have a different asteroid, that number might be different, but you want to take, whatever number you measured in question 2, the time between two successive minima, that was half a rotation period. Okay, then in question 6, you want to estimate how many times brighter the asteroid is when you view it along the wide side as opposed to the narrow side. So this is where we use the horizontal purple line to measure the minimum brightness and the maximum brightness. Well, what we can do here, because we have two different size minima, so some of the asteroids, numbers 1 through 9, will actually have, the same size maxima or the same size minima. But you can just eyeball that. So we can sort of visually take the average by moving the purple line, sort of in between. We're just going to eyeball the average brightness. And this time, the purple line is measuring the intensity. So we're going to look over to the right where it says intensity. So for number 6 we're now, our average maximum brightness is about, so that's the maximum intensity, that's about 0.94. And our average minimum brightness, or minimum intensity, let me just click and drag this. Yeah, I'm just going to eyeball it again, try to put it between, the two lowest dips. I'm just going to try to eyeball that. And let's say that intensity is, so the minimum average intensity is 0.263 over here on the right. Okay, and the brightness, the intensity that we get from the maximum or the minimum, that's basically proportional to the area that we see. So proportional to the wide area would be the maximum average, and proportional to the narrow end would be the minimum average. So we can actually get the variation. Well, of course, I say here in the instructions, use the highest maximum and the lowest minimum. Either way is fine. We take the ratio of those two numbers. So we divide the maximum intensity by the minimum intensity. I'm going to grab a sheet of paper here, and I'm going to pull up a little calculator. Okay. So we're going to calculate maximum, which was 0.94, divide by the minimum, which was 0.263, and that's going to give us a ratio of 3.57. And that doesn't really have any units because you're dividing, intensity by intensity. So we would say that, the wide side of the asteroid is 3.57 times brighter than the narrow side of the asteroid. So that would be our result for number 6 for our asteroid number 9. then in number 7, now we want to compare, well, how much longer is the long axis compared to the short axis. Now, in number 6, the ratio of intensities was proportional to the ratio of the areas. And I'm just writing this down, I don't know why. And then in number 7, now if we just want the side or the diameter, that's just one dimension, where area was 2 dimensions. So we can actually go from area to edge length by taking the square root. And since we already have the ratio of the areas, all we have to do in number 7 is take the square root of the 3.57 and then get by the factor by how much longer the long axis is compared to the short axis.
Okay.
Let's see. Good. Okay, this calculator does have a square root button.
It's 1.89.
So, say again?
Oh, I was saying the square root of 2.57 is 1.89.
Yeah. Yeah, I'm just rounding, 1.89. Yeah, so that would be now so the long axis is 1.89 times longer than the short axis. Okay, and then actually questions 8 and 9, I mean, they're pretty straightforward. They're just supposed to measure, how symmetric the asteroid is. Because in number 8, you're going to compare the intensities of the 2 minima.
Mm-hmm.
And like I said, some asteroids have the minima are all the same depth, or the maxima are all the same height. Then you just divide the same number by itself. But okay, in our case, my calculator went away because I'm trying to grab the line. So for asteroid number 9, minimum 1 would have an intensity of 0.293, and then minimum 2 has an intensity of 0.236. So then the ratio, I'm going to pull the calculator back up. You can just do minimum 1 divided by minimum 2. So 0.293 divided by 0.236. So your ratio would be 1 point, and just round after 2 digits after the decimal point. So 1.24. So minimum 1 would be 1.24 times brighter than minimum 2. And if, both minima would have the same depth and would have the same intensities, then you would get an exact factor of 1. So that can happen for some of the asteroids. And then in question 9, we're just going to slide up to the 2 maxima. So, well, let me do maximum 1 here. Yeah, that's almost at 1. So the maximum 1 has an intensity of 0.993. Maximum 2 has an intensity of 0.9. And again, you take the ratio of the 2. So I'm going to clear the calculator, and then 0.99, didn't get my decimal point. 0.993 divided by 0.9. Okay, that equals 1.1. I'm just going to leave it 1.10. So that means the two maxima are actually more similar to each other than the two minima. But I mean, that just sort of shows you how asymmetric a particular asteroid is. Okay, and that's all there is to, I think that's, say again? Oh, okay. But I think that's pretty much all we need this program for. So the rest we can actually do just, from the lab manual. So let me return to the whiteboard. I'm going to end the sharing. Okay, and I'm going to return this to the, well, it's called eBoard. It's essentially a whiteboard. Let's see, for number 10, what I could try to do is see if I can reproduce the sketch for figure 2. Let me just see if I can, it's probably not going to work very well. Because I don't know if I can copy or paste anything. Well,
Could you just check it out? I know sometimes you write out like a red or a blue marker.
Yeah. I don't know how well we may not be able to use. If I sketch it here, we may not be able to use it as a measure, to measure from. But yeah, at least we'll have sketched it out. Okay. Yeah, let me draw like a little sun here, and yeah, it's not going to look very pretty, but let's say that this is the Earth's orbit. Say this is the Earth. I don't know if I can move it. Nope. Sorry. Okay, and then now we'll do the asteroid orbit. Okay, and now we're going to do the asteroid. Well, maybe I'll put it in blue, just making a little dot there. Okay, so we have, and that's supposed to be like the closest approach. Okay, let me do that again here. Okay, got the, whoops, no, I want to go back to black, sorry. Oops, I don't know why I put it on, went on the square. Let me put it back on the circle, here we go. Okay, so here that's supposed to be the sun. Okay, and that's supposed to be the, and I make it a little bit more circular. Okay. Okay, that's supposed to be the Earth's orbit. And the Earth is over here. And then we'll have the asteroid orbit. Okay, and now the asteroid is supposed to be maybe over here. Oops. Redo that. Oops. Oh, I didn't mean to. I'm sorry. Okay, here we go. Okay, let me just label this. So we know that it's asteroid question 10. Okay, yeah, the question is, how many times brighter is the asteroid in position, I think this is case A. Yeah, case A and case B. So let me just label the two cases. And okay, so here we have case A. And then we have case B. Okay, and the question is, how many times brighter is the asteroid in question in case A than in case B? Well, it says brighter or fainter, but if you look at the two sketches here, the distance of the Earth from the Sun is pretty much the same because, you know, it's on a almost circular orbit around the Sun. So the distance from the Earth and the Sun is not going to make any difference in how bright or faint the asteroid is. Also, the orbit of the asteroid, I mean, since they're all orbiting in the asteroid belt, and the asteroid belt is a fairly circular orbit around the Sun, so the distance between the Sun and the asteroid is also not going to change. So the distances from Earth and asteroid to the Sun are not going to make any difference whether or not the asteroid is brighter or fainter in case A or B. But what will make a difference is how far away the asteroid is from Earth. So, I mean, what would you say? In which case is the asteroid brighter, that we can see the asteroid brighter on Earth?
In which case? It would be brighter on Earth.
Yeah.
Case A.
Yeah, case A, because it's closer. So all you have to do now, in order, you know, to measure this, is to measure the distance between the Earth and the asteroid in case A. You just make a little straight line here, and in case B. And it's pretty much up to you, you know, if you want to measure in centimeter or inches, because we'll take a ratio, so the units will cancel out. Of course, I have a preference for centimeters, you know, being from Europe and being a scientist. Okay, so you would measure from center to center. And again, you don't measure on my sketch here because that was freehand. That is not to scale. but you measure that in the lab manual on page 13-10, figure 2. So let me call this DA, so distance A, and we switch back to the pen. No, I wanted a straight line, because you're supposed to measure with a ruler. Okay. And we're going to call this dB. So the distance for case B. I don't know if you have a ruler right there.
If I have one.
Well, actually, what I can do, I can just use example numbers, because I don't have a ruler right here either.
Mm-hmm.
So I'm going to make a note here that I'm going to use example numbers that are going to be different from the lab manual.
Okay.
No.
Well, the distance from the asteroid for case A is about 3 meters.
3 centimeters?
Oh, yes.
Yes. Okay. Well, what do you get for case B?
Case B from Earth to asteroid is about 5 centimeters.
5 centimeters? Yeah. Are there any millimeters too, or like 3.1, 3.2, or?
Well, itself is about maybe 0.3. So I didn't know if you want us to go from the edge of Earth or beginning of Earth or the center.
Well, center to center.
Okay. Well, center to center. It's about 4.7.
Okay, it's 4. What? Oh, is that for case B?
Yeah, for case B, about 4.7.
Okay. 4.7. Okay. And for case A, it's pretty much 3.0.
Measuring again from the center, it's about 3.1.
Oh, okay. Okay. Yeah, let me just do 3.1. Well, let's just go with 3 for now. Okay. Okay, and the brightness is inversely proportional to the square of the distance. I'm just going to make a note of that. Let's see right here. So to the square of the distance. So if an object is twice as far away, like a flashlight, you would only see it a quarter as bright as, if it were 2 times closer. So that's why, the ratio of how many times brighter the asteroid is in A versus B, that's going to be equal to, I'm going to just write this out as a formula now, equal to, well, how much further B is squared, so the distance of B squared divided by the distance in case A squared.
Do you actually run something for the bottom?
Say again?
Because I'm looking at the screen and like I can only see the top letters. So when you're writing, I just didn't know if I was going to be able to see it later.
Oh, do you see the blue type that I just typed out in blue?
Yeah, I see that. I can only see like the top letters. I can't see if you're writing anything. I really.
Is there a scroll bar on your window?
Oh, not for this.
Well, yeah. Let me type it in. Well, I can type it in.
What I was saying. You go ahead.
Yeah, I mean, I can also type it in the chat window.
Okay. Oh,
so,
yeah.
So that
Yeah.
You see it?
I know whether or not I'll be able to see it later. But the
Okay.
other lesson that we were doing, that was fine for me to screen up and down. But this one is just not letting me see that.
Okay. No, that's fine. I can type it. So what I'm doing now, because the brightness is inversely proportional to the square of the distance, that means that the brightness ratio is directly proportional to the inverse square ratio of the distances. So I'm going to square the distance in B because that's the longer distance, and I'm going to divide it by the square of the distance in A. Okay, and I just typed it into the chat box too. So with numbers, I'm going to put that in 3.0 centimeters squared divided by 4.7 centimeters squared. I'm going to also type that into the chat box. Here we go. So 3.0 squared divided by 4.7 squared. Okay, I'm going to pull up my calculator again. And of course, this is not a very sophisticated calculator, so I'm going to calculate the squares separately. Well, okay, I know that the square of 3.0 squared is equal to 9. But let's see, let me go ahead and
the other one is 22.09.
Oh, okay, 22.09. Oops, wait a minute, I typed in the wrong thing. We wanted dB squared over dA squared, so I'm going to actually have to delete that. I'm sorry. Let me back up. Not what I typed in was dA over dB.
A.
Yeah. See, if I talk at the same time and type, that's what happens. Let me back up here also on the slide. I'm going to type that in again. Okay, so we actually want the 4.7 squared divided by the 3.0 squared. Okay, I'm going to retype that in here. 4.7 squared divided by 3.0 squared. Okay, so now we can calculate that, and that's going to be 22, you said 22.09? Actually, if you don't mind, can we just finish this calculation and then I jump off and we can do the rest maybe by email? Because my son and my daughter, they have CRCTs tomorrow and they want me to bring them to bed. So yeah, let's just go ahead and finish this calculation with question 10, or yeah, and then we'll just talk about it by email. Okay, so we have 22.09 divided by 9. Okay, so that's 2.45. And that's again just a ratio, so it doesn't have any units because the centimeter square will cancel each other out. Yeah, so that means asteroid, the asteroid is 2.45 times brighter in case A than in case B. And I'm just going to write that in here, 2.4 times brighter in A. Okay. All right, yeah. Let me jump off. Also Wednesday from 8 to 9, I'll have another chat session, and that's the official one. Would you be able to come back then?
I work Wednesday, Friday night,
Oh, okay.
Would you be
well,
able to
I mean,
do
I can.
it tomorrow?
I'm not sure if I can do tomorrow. I think my kids have a game. I can send you a sample calculation by email and see how far that'll get you. Let's see, I'm trying to think. Well, I mean, if push comes to shove, you could turn in the labs a little bit later than the last day of classes. So I wouldn't strictly hold you to that.
Okay. Well, to see if I can maybe get someone to cover my shift on a Wednesday or Thursday, so that I could try to make it to the 8 o'clock, if not, I come up here to the school all the time to get help, so I'll just work on it as much as I can and email you back.
Yeah, I think the rest we might be able to do with email because it's just calculations. It doesn't, you don't have to look at any images or figures anymore for the remaining few questions. Yeah, let's see if we can do it by email. Okay, I'm going to stop the archive.